That's the title, of course, and co-author is Manuel de Jesus. I usually call him Manu. Yes, and the motivation is this one. You know, is I have been interested for many years in process-driven type of explanations of patterns of vegetation, and I will try to go fast to leave time for questions. And one example of this, a classical example, is savannas, which we have seen here several times. This is from the paper of Todd, Scanlon, and some years ago, I don't even remember what year it was, 2007. And let's not target if those are power laws or not. That was not the point purpose of Todd's paper. Particularly, I believe that they will not hold water to be an strict power law if you make the analysis. But that's and I will be ready to argue that too. But because they are close anyway, and this is less close. But you definitely have patterns in there, and how to explain there? You know, there are other ecosystems. I will come back to that example in a little bit. You can always produce models that several automata or other types that will. Perbach was the master of them all in this type of thing. You know, that the game of life, the fire propagation game, many games that will give you real power laws. They extend for 10, 5, 6, 8 log scales. But there are other ecosystems, and specifically river basins, in which hydrology, you know, is so fond of them, in which I suspect, or some of us suspect, should have also patterns of vegetation, not as evident as those in savannas. And these other ones, different river basins, for example, have strong gradients in hydrology, strong gradients in temperature, and these type of things, that make the analysis a different type of thing. Are there general principles behind this? That's a very open question still. Some people, especially credible players, use Dewars in Australia, and Alex Claydon, Germany, have done a beautiful job in trying to suggest maximum entropy production as a general thermodynamic principle that could explain some patterns in geosciences. I say, well, from the strict physical point of view, this is a much debated point still. It's not something that, you know, that can be taken as the gospel of the Lord. But certainly it's a very suggestive thing, and there seems to be some basic physics theory coming to the point that it may be true that maximum entropy production in far from equilibrium open systems is an organizing type of thing. Remember, this is not Prigogine type of analysis, in which are close to equilibrium type of thing. Okay, this is a different type of analysis. I will not get into that. Now, for what is important in this case, you know, maximum entropy production is, you know, you go through every kind of process that leads to entropy production in an ecosystem or in a river basin or whatever, and that is not a simple thing to do. If you read through many of the papers of Claydon and Dewars and some others too, in savannas especially, or in a semiarid system, I would say arid and semiarid system, the thing may be a little bit simpler, because probably the dominant cycle of the dominant process of entropy production are those related to carbon assimilation. And as shown clearly by this is adapted from Dewars, paper of Dewars, or Dewars, I don't know how to pronounce that, is in blue, photosynthesis, what inputs entropy into the system, entropy production. These are the two outputs of entropy, and these are different types of entropy transformations inside the system. What I want to point out here is that maximum entropy production, from the point of view of the carbon assimilation cycle, is equivalent to maximizing carbon assimilation, which is something which ecologists and hydrologists have played with the idea, at least from at least in arid and semi-arid ecosystems, as a sensible thing to do, as a sensible guiding principle for nature. I'm going to apply that to the Rio Salado river basin. These are the characteristics of the Rio Salado. It has a strong precipitation gradients. This snow line is a very important factor in the distribution of precipitation. I'm sorry, the distribution of of spatial distribution of vegetation, because it controls the initial conditions of the growing season in terms of soil moisture. I like modeling, so what I prefer to be faulty in the modeling than just to talk about the distribution of the vegetation. So I will take that path of action in this case, and these are some characteristics of it. In here you see the distance from the outlet, and this is, I don't know what this is, the average evapotranspiration computed with very detailed modeling, pixel by pixel, 25 meters by 25 meters, okay? This is what we call a power law, by the way. 1, 2, 3, 4, 5 log scales, very straight. This is real data, but this doesn't have anything to do with entropy production. Well, could be anyway. But this is just from the geomorphology. This is the probability of the area, contributing area to a randomly chosen point in a basin. That is a random variable that has a power law and that has been very well established. And this guy, the exponents are on 0.43, 0.45. And that comes from geomorphology, and the fractal structure of river basins, in fact, are responsible for this power law, which is a power law. I don't care what river basin you're analyzing. If I take the random variable cumulative area to a randomly chosen point, that is the law. It will shift in position, but that is the exponent. Now we are going to apply the hydrologic model to the Rio Salado river basin, pixel by pixel, 20 meters by 20 meters, in which we are going to do the full thing. We are going to have the dynamics of precipitation as a market Poisson process. We are going to have, during the growing season, the whole soil moisture PDF distribution, the probability distribution, and that we know from the past. That's the steady state. Very importantly, we will not remain in the steady state. The initial conditions to the growing season are very important in terms of soil moisture, because there is snow accumulating, and then there is an important quantity of soil moisture that is there at the beginning of the growing season. So that's a transient that doesn't make this completely valid. We have to account for that, and we did. In fact, I will not get into the details that have been published before, and this is also in the book with America. Okay, these are parameters of the model: rate of storm arrivals, etc., soil properties, vegetation properties, etc., pixel by pixel. Now, what we're going to do is in every pixel see what type of a tree. There are 3 dominant types of vegetation. There's the Latin names are irrelevant. One are trees, the other ones are shrubs, and the other ones are grasses. And in so we will start with a random type of distribution of vegetation in a basin, and then change the vegetation to one that increases the whole assimilation, the whole transpiration on the river basin as a whole. If we make a random change, and if it doesn't increase it, we reject the change. If it increases, we keep changing the thing. Typically what you do via simulated annealing, okay? And this is the thing of simulated annealing. Of course, with simulated annealing, we have the chance to either go what is called the ground state, trying to get the absolute optimum distribution of precipitation, the absolute optimum one that maximizes the transpiration on the whole thing, or assimilation in this case, in fact, because we had measurements of water use efficiency in this system. There is a LTR in there. Or what we go through what is called feasible optimality. Nature, frequently doesn't go to the absolute optimum, very close to the optimum. We do that via simulated annealing. Sometimes this parameter is called the temperature parameter, but it's just to account for feasible optimality. And this is the vegetation observed. This is the ground vegetation. The ground state is the one that maximizes. It doesn't look good in there. Okay. Anyway, this I have some other slides that do better than this. That the ground state, the one that will produce the maximum assimilation, this is the one that is the maximum assimilation via simulated annealing. So you give a little bit of flexibility to the thing, and this is the one. Simulated annealing at very high temperatures, meaning very random type of thing. More important, okay, this is a more detailed type of analysis. In this line, the red lines are cell profiles of vegetation. Why I like this? Because this is a river basin. The vegetation tends to be organized around the network. So in here is distance in pixels through the outlet, and here are numbers of pixels that have this type of vegetation, meaning trees, grasses, or shrubs and grasses. And you immediately see that for example, the ground state, the very optimal one, will have more shrubs that are really observed, but the simulated annealing one, the one that gives some flexibility to the process in terms of accounting for feasible optimality for things that are close to the optimal, not quite there, but it's really what you have in nature, follow very well the profiles of vegetation. That's a way to describe the organization of vegetation through the network. This slide I like, because in here you see, this is again for the Rio Salado River Basin. In here you have the sum, really here should be sum of Q sub I, but we don't have the measurements of Q sub I. Here it should, and this comes from a parallel, something that has been observed metabolic analysis in living organisms, in animals and humans, etc. When you have a network, like for example the veins, transporting metabolites to a surface, there's an optimum way to do that. And what has been observed is that the metabolic rate, which for me in the case of Salado would be transpiration, let's call it green metabolism, transpiration. The metabolic rate in the organisms is a very nice power law. This is not distribution power law PDF, it's just a functional power law. And here is all the volume of blood, in the case of a living being, of the blood that is present at the system of the drum. So this sigma sub A sub I should be sigma Q sub I, meaning the sum of all the volumes of water that are present in a subbasin at the moment. So I get a subbasin, I have this subbasin network, and since I don't have the different Q sub I's, I will have to have a station in every link. I will say that the typical, the average mean flow is proportional to the area, and this sums all the different sub-areas in that subbasin. That's a surrogate variable of the volume of flow in that subbasin at any given moment. And the theoretical law for living things is you put here Q sub I, and this will be two-thirds. And here is 0.67, very close. This is the theoretical result is for a two-dimensional metabolite distribution in which the velocity of flow is a constant. The metabolic rate versus the volume is follow this law. Why I think this is important? Because if it were to this is really very nice fitting. Huh? By the way, this thing here says this is the real one. The real one. This is the real one. The optimal one from optimization is the dash line. It's a little bit above. But if I use other types of river basin, which I put the distribution of vegetation in the different form, they will be below that. So the river system and the vegetation tend to go to this type of optimal arrangement for the metabolic transformation, this being green metabolism. And the fitting, I could not ask really for a better fit than that. And there is not fudging with this no R square or trying to maximize or anything like that here. And you can repeat that. They have been repeated in several river basins. And this has a very serious theoretical parameter. Now the practical implications are the following. If I want to know transpiration, not evapotranspiration, no, transpiration, which is always a mess at the ecosystem scale or at the basin scale. If I know the map of the basin, even if I don't know the discharges, and I substitute the sigma Q sub I by the sigma AIs, as I say here, I can in every point sum all the subbasins, the areas of the subbasins embedded to that point. That is going to be this line. The only thing I will not know is where to locate this line. But that exponent is very much fixed. That has, I have to go to the thing, but that has strong implications in how to compute transpiration at the river basin scale or transpiration at the ecosystem scale, which is it's a $64,000 question, The type of transpiration is something. Transpiration is something very different. Now, those in the river basin. Let me go quickly to savannas for a moment, okay? Savannas are very different. Savannas present frequently this type of clustering things, in which, let's not get if have power loss or not, but certainly in some cases have power loss, in other cases it may not be, maybe some different kind of fat tail. The distinction may or may not be important according to your purposes. if it's to reproduce the pattern in the basis of process-oriented thing like Todd, I think it's not important to say, hey, it was a power law or not. The question is, did I reproduce it or not? And in his case, he's using a process-based model with a global type of driving mechanism, which is rainfall, and a local type of facilitation, which is the dispersal of seeds and these type of things. Now, a different type of question could be maybe a little bit out of the mill or out of the usual type of question, but I like to ask those is, why are they so common, those clusters? Why they tend to exist so frequently? Maybe there is a reason behind that, much beyond mechanistic type of models. Maybe nature is using that because it's the optimal spatial structure for some type of metabolic thing. For example, hypothesis. I could say, oh, nature likes fractality. Well, by the way, fractality will imply real power loss, not approximation. Real power loss. Let's assume for a moment the real power loss. If the real power loss, I could put a hypothesis, maybe nature likes that fractal type of arrangement because it maximizes the green metabolic activity of the ecosystem. This is a hypothesis, but could be tested. Now, it's not that easy. It's the same thing that the question in river basins. Why river basins have the structure they have, which is fractal. And it's fractal not only in the drainage network itself, it's fractal in the metabolic structure too. But it's fractal because it responds to criteria of minimum energy minimization in terms of transporting flow from every part of a river basin to a single outlet through a tree type of structure with no loops. So the same type of questions could be put in savannas. Now, to analyze that question, which is a very difficult question to analyze, one will have to start with two things. One is to pose models that reproduce that and then go further than that. Then try to say, in a more or less theoretical basis, more or less because one will have to take some leaps, what is the transpiration or assimilation associated with the different types of structures one can pose in there. Two types, very quickly. Poisson model and Mechanistic model. In the Poisson model, you have an average tree density, and then the 2D structure of a Poisson model is very easy. Poisson located, that means uniform, given the number from a Poisson distribution, they are placed uniform, and then you put a canopy. The canopy, you can put an exponential distribution in the canopy or whatever, in the average crown radius. Or you can put a Pareto distribution if your variance is very large in the canopy radius. And the other one, well, in the Poisson model, it's a very restricted one. We like it because it's very simple, but it's extremely restricted. Once that you put these two parameters, the average radius of the crown and the density of trees, the vertical structure is fixed. No monkeying around there. It's fixed. In fact, that immediately tells you at a randomly chosen point what is the distribution of the number of overlapping canopies. And if I do the same thing for the roots, what is the number of what is the distribution, which is Poisson, by the way, of the distribution of the roots existing at any randomly chosen point. But that doesn't tell you anything about the transpiration. Now, it's a very restricted model, but it's one easy to deal with. The other one is the let me go fast, is the Tiemann-Scott model, in which we put the trees clustered among themselves, and I will not go into the depths of the two-dimensional Tiemann-Scott model, but it's a simple model also, and then we put the crown with a certain distribution of crown. Remember, what is observed in reality is the distribution of sizes of canopies, not so much of trees. What you get from the images is of canopies. Now, if you, let me show you some, let me skip this, but I can, incorporate leaf area index, number of canopies, number of roots, that mathematically can be done. But then, let me go to the figures. The problems start things like this. These two trees and these two trees are very different for the landscape function. These have an overlapping here, so the canopy coverage is different. Now, if I try to make the canopy coverage the same you know, increasing this with this thing, which also overlapping here with this little one, now I have different density of trees. But I can always match, in fact, via a Poisson or a Niemann-Scott, the density of trees observing the field and the canopy coverage observing the field. Those are easy to match. The vertical structure, nevertheless, in the Poisson, I can do nothing about it. It's fixed to me after I do that. Now, okay, thank you, because now I want to finish in 5 and leave some time for discussion. This is Tashanin, you know, who says, well, that's the way it goes. And this is, in fact, this is the distribution. See, this is what you will adjust probably. This doesn't come from any model. That's what we'll adjust via, you know, an R square or something like that. Now, in a Niemann-Scott, this is Tashanin again. In a Niemann-Scott, you see from here to here, you can say that's a power law. I will very much doubt that I could sell that to a physicist as a power law when I see this part here and this part coming here. But they have one log scale here in which I can. But, you know, power laws should go over the extended range of spatial scales. But the fit is really very, very nice of a Niemann-Scott in which I'm using a Pareto distribution for the crown radius of the trees. Now, nevertheless, if I use a Niemann-Scott with an exponential distribution for the radius of the crown, it's not that bad. It's not as good as the other one, but it's not that bad. And this is bad. This is Poisson with a Pareto in the distribution. This is let me go. This is Mongu, and again, it's not bad. Niemann-Scott with a Pareto distribution there, and Niemann-Scott with an exponential. Here is Poisson again. Main message here: if I want to fit the density of trees in a savanna, if I want to fit the canopy coverage distribution, the density of trees, the total canopy coverage, and the distribution of the clusters of canopies, I can do it with different models. And they do decently well, but they represent very, very different things. You see, when one tries to go to a model and say, look, I want to see what this means in terms of the ecosystem scale, which is really what is the challenge is. We can analyze one tree, and we have done that with stochastic rainfall and leaf area indices and so on and so on and so on. But when you go to the ecosystem scale, you know, I'm sorry, but mechanistic models simply that, you know, move one thing to the other will not allow us even to approach crucial questions like what is the transpiration of the ecosystem, what is the assimilation of the river basin, are beyond that. And I think those are the frontiers, or one of the frontiers in which I will put a lot of emphasis right now. Now, I tell you, we can do that, mathematically speaking, for any of these models. At a randomly chosen point, what are the numbers of overlapping roots, or roots intermixed there, and the number of overlapping canopies? That will not solve the question either, because these canopies belong to other trees, and the extraction of water from these roots not only depends on the number of canopies and roots that I have on the site, but it also depends on where is this tree located and its own surroundings, and this tree is depending on the other one. The whole system is connected. How to do that? That's a challenge. I will not go into that in here, but that's what we are trying to do. I will close right now in order to leave questions, but that's where I think we are in this thing. I'm really pushing and a fan of process-oriented models much more than any other type to solve what I believe are the real crucial questions for studying patterns of vegetation in arid and semiarid ecosystems. Thank you very much.
We have time for a few questions.
Sure.
Yes?
Thanks very much, Ignacio. Wonderful enthusiasm and data combined, which is cool. With respect to this maximum entropy thing and any sort of optimal configuration, a couple of things come to mind. First, for instance, bistable states. We've seen a lot of bistable states today, which had very different productivity. And that, to me, argues that this is perhaps a questionable thing. As well, if you think about canopies that intercept water just to fault other plants of getting water as a competitive strategy, this also would not maximize any sort of productivity. And one of the things that also, when we look at these patterning, I'm thinking back to the hummingbird population question. It turns out hummingbirds do not like to jump across patches. And so they percolate through and then they are often required to pollinate specific species. So I'm thinking of the Costa Rican example. And so all this put together, I guess, argues to me against some of these gross simplifications. When we're dealing with biological systems, there's often a subtlety and a complexity put together and that operates at particular scales that are very invisible.
Let me answer that quickly. I don't think this is much more complicated than some of the systems that physicists deal with. Atomic and subatomic systems. And thermodynamics is a science that in which holds true. Now you say, you put the canopies and so on. Of course, canopies have many effects. They intersect more, they shade more. And, now the question is, do you think those they interact in some kind of globalization thing? I wouldn't say always they do, but I will say they tend to do. My example is the following. It's the same type of question that I received several times when we were doing drainage networks. And do you really believe they respond to general systems? Yes, and I think it has been proven. It's minimal energy minimization. And now, there is an infinite variety in there, but the principle is clear. Now, does this principle hold here in terms of maximum entropy production? I don't know, but don't get hold on in the name. Hydrology have many times dealt with, let's try to maximize transpiration, which is, green metabolic activity, really. Okay? Do you think it's for example, in human organisms, that's a well-established fact, is the growth of metabolic activity versus volume of flow at the moment is 2/3, period. And having proven mathematical and physical and full experiment. That is a complicated system by itself. That's a cellular system with a lot of ins and outs. Can somebody like that be going in here? That 2/3 feet, which has been repeated in several basins, that's very exciting. And, we have always dealt with the question, how to separate transpiration from evaporation. And people, and I agree with all this, take a single tree, get the hash of it, and so on and so on. Honestly, I am all for that. But I'm much more interested in the landscape scale. How is that going to help me in the landscape scale if I don't come with some kind of organizing principle from above? Now, is this the gospel of the Lord? I don't know, but I think it's worth to investigate. At least the question is an important one. I don't want to fall in what we were talking the other day about Wolfgang Pauli said, how was the speaker? And he came out and said, it was not even irrelevant. I'm sorry, he was not even interested, I prefer to be wrong, but let me deal with the important questions, okay?
Jeff, please.
Thanks, Ignacio. So, Gabby and Mielker and I and a couple of others had a small workshop on eco-hydrology at Duke, I guess it was back in February. And we invited Adrian Bejan from Duke University in Mechanical Engineering, who has this constructal theory that speaks to fractal river basins, branching hierarchical networks. I wonder if you might comment on that, if you're aware of some of his work in the context of your remarks today.
I am vaguely aware of it. I have read a little of some of the things of Basin, and I haven't read his book, to be honest. I have it, but I haven't read it. His is a very geometric type of theory, okay? So the tree goes on, and that has been used also by ecologists. Brown, Enquist, and
West.
Right, I always leave somebody out, okay? It's more or less that without the name.
Mm-hmm.
But it's that without the name. The application of that to river basins, we are coming to the same thing. It's going to optimize minimum energy expenditure. I prefer to deal with it straight, like it is, as a random system. I am not saying that he's wrong in that. I think that, since ours is much more straightforward, was done way before, and it fits beautifully well, and has a very much physical basis.
Danny, if it's a quick question.
No, I have never a quick question. Ignacio,
Sure.
first, there is still controversy about the 3/4 metabolic law versus the 2/3. You know that. Dodd's paper, I'm looking at it at PRL, give a very nice historical. So it's not yet the truth.
Absolutely.
Okay. My question is different. I'm asking myself.
By the way, I'm out, because I will put a comment there. This is the 2/3. There's no controversy if you are using a two-dimensional system.
Versus 3D.
Absolutely.
Okay. So.
Okay? And the river basin is much more a 2D system than a 3D system in terms of the elevation with respect to design.
Okay, fair enough.
Very clear.
Yeah. My question is about the arguments we heard earlier today about percolation, and also you invoke it. You can invoke similarity between river networks that are convective networks that move things in the 2D space, and percolation that is also supposedly percolating in 2D space for objects that are actually operating in the other dimension. If you think about plants as working in the 1D that is transverse to your 2D plane that we are now modeling, how is exactly this is working? Because I think mechanistically there is a dimension mismatch here.
I think the only way, and that's why I tried to point out at the very end, the only way to deal with that is to go with a process-oriented model that takes into account roots and canopy distribution and tree position. Okay? Now, I can use tree position with a Poisson model. I can use tree position with the Niemann-Score model. I can use whatever you want for the radius of crowns and so on. Mathematics of that can be done. It can be a bit more complicated with the Niemann-Score, but it can be done. I can tell you what is the mean and the variance on the number of canopies at any randomly chosen point if they follow a 2D Niemann-Score. The same thing for the roots. But what I cannot do is to tell you how much is the evapotranspiration on the landscape scale. Because it not only depends on that, it depends, as you say, of the interlinkage between the two. I have so many roots here, so many canopies, but where are the owners of those roots, which are the ones that are pumping the water? Okay? That, to do it from a general type of model, is proving very challenging. We're doing right now, carrying out the analysis, brute force, to be honest. Via simulation, and then simulated the thing, put in the tree, doing a 20 by 20, full analysis, by the way, with full dynamics of precipitation, because I will not buy it again if you tell me the average rainfall is so much. I know plants respond differently. I need to put the dynamics of rainfall into the game, or I have no, my transpiration values and a simulation value will make no sense. But I don't have the right answer for that yet.
Thanks, Ignacio. Unfortunately, I have to stop the conversation. My talk is the last one, and I appreciate the intelligence of the organizing committee. If I give too much time to other people, I won't have time to speak. So, thank you so much.